I think you might want your formula sheets out just so you can kind of follow along with where we're heading. And what we're going to look at today is how a generator works. Almost all generators involve some kind of circular motion or circular crank, and here is why. Okay. The generator was invented by Michael Faraday. He called it a dynamo. That's what they call it in Britain. The previous figure shows a very simple hand-operated generator with a coil consisting of only one turn in order to simplify the explanation. So I want you to notice what's happening here if I turn this in this direction. Specifically, I want you to notice what's happening to this little positive charge sitting in that piece of wire right there. Now you kind of have to look down the end of it, so Mitsu, use your imagination. Actually, no, I can do that right here. If we look down the end of it right here, if you look at diagram A, so here's our positive charge, and right now we are cranking it so that it is moving in that direction. Which way would that charge experience a force? Well, let's see. If I point my thumb in that direction, and I point the magnetic, oh, you know what? Is it going in the same direction as the magnetic field? It won't experience a force right there. It won't feel anything right there. You will not generate any voltage. If you hooked up a voltmeter, it would read 0. But how about right here? If there's a positive charge, now if he's turning around slowly, Sean, now he'd be moving downwards. So all of you point your thumbs down the page. Magnetic field is to the right, so thumbs down the page. Magnetic field to the right. I kind of got to bend myself this way. Do you see that on this side, the charges would be pushed towards us? Oh, but over here, this guy is moving upwards because it's spinning. On this side, point your thumb upwards. Magnetic field still to the right. It'll get pushed away from us. And what that's going to give us, if I go back to my 3D diagram, Mitchell, it's going to give us current going like this, around and around and around and around and around. Of course, now we'll hook it up to a circuit and bleed that current off somewhere and do something with it. This is why we have alternating current coming out of plugs, because it's easiest to create alternating current. In fact, what happens is, when you're turning the generator, when for a split second the generator is moving parallel to the magnetic field, you get no voltage. When it's moving perpendicular to the magnetic field, you get a maximum voltage that's positive. Then when this rotates underneath, you get no voltage again. Then when it rotates back to here, you get maximum voltage, but now this arm used to be coming towards you. Now this arm is moving away from you, Brianna. You get a negative voltage. This is why we get alternating voltage from plugs. A generator, it's much, much easier to create alternating current. It naturally creates alternating current. So when the coil is rotated, the two long sides of the coil cut across the lines of force of the magnet, and a varying EMF is induced in these two segments. Those that are in Math 12, the EMF goes this way, then this way, then this way, then this way. Hey, Math 12, what kind of a function is that? It's sine or cosine. As a matter of fact, the amplitude is the voltage. The frequency is, we get 120 hertz. The period is 1 over 120 coming out of the plugs. Sorry, 60 hertz. 1 over 60 is the period. So can you see you go from 0 to max to 0 to negative max, back to 0 to max to 0 to negative max. Is that okay, Kayla? Makes sense? Looking at a side view? So when the coil is horizontal, like in 8.7b, the segment in which an EMF can be induced is moving perpendicularly. You get maximum voltage. When the coil is perpendicular, the top segment is moving parallel to the speed, like right here, you get no voltage. Blah, 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 blah. Turn to this page here. So Faraday had already, Brett, moved a single wire through a magnetic field and noticed that he could separate charge and induce voltage. And he had invented the dynamo, the generator. He'd said, hey, Connor, I can spin it and induce voltage. Then he asked, Maybe those are the same thing. Maybe there is some way that I can link both of those in one explanation. This is where we say, Faraday, you are brilliant. Here's what he said. How can we combine induced voltage in a wire and induced voltage in a loop of wire? Consider the following example. We have a rectangular loop of wire and it's moving to the right perpendicularly to the magnetic field. What do these dots mean? Which way is this magnetic field coming? Out of the page? Okay. Where will there be an induced current? Will there be an induced current at location A at all? Well, is there any magnetic field at location A? No. What about location B? Well, let's see. Specifically, I want to look at a positive charge right there, right there, right there, and right there. Which way are all four of these positive charges moving? Katie, what's the velocity direction? To the right. So all of us, let's point our thumbs to the right. Which way is the magnetic field? So kind of bend your fingers this way, out of the page towards you. Which way will this charge get pushed? Downwards. Which way will this charge get pushed? Downwards, but you really can't separate charges in that thin wire, Andrew. Which way will this charge get pushed? Downwards, so you really can't separate charges in that thin wire. This won't induce a voltage. What about here? Well, this charge is not in the magnetic field yet, so it won't feel any force. The net force, if I think about all the ones that cancel out, I will get current flowing that way. There will be a voltage induced, a current induced in area B. What about in area C? Well, again, let's put a positive there, 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 there. Which way will this positive, this front positive, which way will it feel the force? Remember, down, I agree. Which way will this feel the force? Down, but it can't really go anywhere. Which way will this feel the force? Down, but it can't really go anywhere. Which way will this feel the force? Emily, down. Can you see the two currents will push against each other and cancel each other out? See it? Turns out you don't get a current there. When you're totally in the magnetic field, you no longer get a current. It's only when you're partly in the magnetic field that you get a current still. What about location D? Matt, location D is the same as location C. Nuh-uh. Oh, what about location F? The far one. Is there any magnetic field there at all? Nuh-uh. What about location E? Well, again, let's look at these four charges. Has the front arm, has the front part of this rectangle left the magnetic field? So will it experience any force at all? Nope. These two will be pushed down. They can't go anywhere. Where will this guy be pushed? Down. And you get a current going. And do you notice it's the opposite current that we started at the beginning? You see it, Joel? And Faraday asked the question, he said, why? What's going on? He said, I know what's going on. I've thought of a way to link this. To explain this, Faraday realized that a voltage and therefore a current in a coil was induced when the area of the coil that was exposed to the magnetic field changed. This leads us to the concept of magnetic flux. I remember watching Back to the Future, the flux capacitor. Well, flux is a term in physics. Magnetic flux is a type of flux. Magnetic flux is the number of magnetic field lines that pass through an area. It's the number of magnetic field lines that pass through an area. It's the number of magnetic field lines that pass through an area. Look up. No flux, Small flux slowly increasing. Max flux, max flux. Big flux slowly decreasing as you leave. No flux. Symbol for magnetic flux. A TIE fighter on its side, if you're a Star Trek fan, Star Wars fan. I'll be honest, that's the official typewritten symbol, but most of the time we drop the vertical and the two horizontal bars. Units? Well, all flux is measured in lines. There's electric flux, there's all sorts of different types of flux. Light flux, sound flux, all flux is measured in lines. But magnetic flux is measured in Webers, symbol capital W, lowercase b. How do we calculate flux? If you want to find the number of magnetic field lines that go through an area, it depends on two things: how strong the magnetic field is and how big the area is. It's the magnetic field strength times how much of the area is exposed to the flux. Example. Look at picture A, picture B, and picture C, and this is supposed to be a side view of a coil. So you can imagine, instead of a coil, I just imagine a roll of masking tape. This is what we're talking about here. Right now, we have maximum flux. As this slowly rotates, how much magnetic field passes through this coil? Less and less and less and less, until, what's the flux right now? 0. If you want to use an imagination, Brett, I think of it actually, instead of a flux, I visualize a flashlight projector. Right now, lots of light is going through this piece of tape. As I slowly spin it, less and less and less, and there's 0. How can I get more flux? Well, a basic way is, there's several ways. I could get a brighter bulb, or move the area what? Closer to the magnet, if we're talking about magnetic flux. Because now, wow, all the light goes through it as opposed to just that much light going through it. I can get more flux by increasing the area if I had a bigger roll of tape, like a hula hoop instead. More light, more flux, more lines of magnetic field will be going through it. Okay? So there's 3 ways to increase flux. Stronger magnetic field, move closer, bigger area. So in answer to this question here, we would say this. The flux, Andrew, is going from max decreasing to 0. Good physics word. What did you learn about today, honey? Magnetic flux. Flux does not cause voltage. Flux does not induce current. But we need the concept of flux to talk about what the heck is going on in this diagram here. And you notice now I've started to link, Arvinder, a spinning generator. See it? I've started to, now I can start to spin instead of simply moving a wire horizontally. Example, turn the page. Describe whether the flux is increasing, decreasing, or constant in each case below. So in situation A, if the magnetic field increases, what would happen to the flux? Keeping in mind that we said that flux was equal to that times that, which is on your formula sheet, yes? Jacob, want to give Connor an elbow? What's happening to the flux here? Increasing. Flux is increasing. There's my symbol for increasing, an arrow pointing upwards. Joel, what do you think my symbol is for decreasing, an arrow pointing? Okay. What do you think is happening here to the flux? Joel? Yeah. Another way to change the flux is to decrease the area. What's happening to the number of magnetic field lines going through this area as I slowly move it out of the magnetic field? Increasing, decreasing, or staying the same? Decreasing. We'll come back to D in a second. What about E here? Are the number of magnetic field lines increasing, decreasing, or staying the same? What about if I move the magnet closer? What if I move the magnet closer? Increases. What if I spin the coil? Ooh, now we can start to talk a little bit about how a generator works. As I spin the coil from this, what's happening to the flux traveling through this coil? Decreasing. I find, by the way, this analogy, I can wrap my brain around it and just imagine, right? Flux is decreasing. What if I squeeze the loop smaller? What if I go from a bigger piece of tape to a smaller piece of tape? Decreasing. Here we have a circuit and a loop of wire next to the circuit. Which way is the current flowing? To the right? Is it creating a magnetic field? Yes, this is our right-hand rule for a current, so all of you point your thumb to the right. Your fingers curl in the direction of the magnetic field. What direction is the magnetic field down here? Point your thumb to the right. Your fingers curl, point your thumb to the right. Yes, I'm talking to you too. Fingers curl in the direction of the magnetic field. Which way is the I'm sorry, to the left, to the left, to the left. Good gosh, guys, my bad. Point your thumb to the left. Thank you, Brett. I'm yelling at Emily, it's me. I'm sick today, okay? Which way do your fingers curl underneath the wire here? Are they going into the page or out of the page? Mine are coming out of the page towards me, yes? Yes? So the magnetic field here will be this. What if I beef up the current? What do you think is going to happen to the magnetic field? Bigger, so what's going to happen to the flux? So another way to increase flux is to increase the electromagnetic source of the magnetic field. Now, what about this one? What Faraday realized, he said, oh, hey, wait a minute. There is an area when you're sliding a bar. Where? The area behind the bar that you're leaving behind is increasing. The flux here is increasing. That's what's going on. That's how he was able to link spinning a coil with sliding something sideways. He said, you know what? There is an area there. It's the area behind the object. Previously, we had said that an induced voltage was created when we changed the field orientation or the area in a field. We can now state it more simply. Voltage is created when flux changes. Constant flux, no voltage. Changing flux, changing voltage. In fact, Faraday found this. This is called Faraday's law. He found that it related directly with the flux change. The bigger the flux change, the more voltage. Inversely with time, the smaller amount of time, the more voltage. In other words, the faster you change the flux, the more voltage. And he also found it varied directly with the number of loops of wire. You want to get twice as much voltage? Instead of one coil, use 2 loops of wire. You want 100 times more voltage? Use 100 loops of wire. Faraday's law. The induced voltage, EMF, created in a coil or coils of wire is given by equals negative N change in flux over change in time. This is on your formula sheet, yes? Okay, it's Faraday's law. This is how it explains how a generator works. This is how many volts you can get from a generator, where N is number of coils of wire. Flux is magnetic field times area. Oh, what's change in anything? Final minus initial. I'm not going to bother you dignifying writing that. So it's change in flux. Make sure you go final flux minus initial flux. And, oh, what do you think delta T stands for? Change in time. That's why the smaller the time, the faster I crank this generator, the more current I generate. Or, if this generator had more coils of wire in it, it would generate a faster current, although I would also find it tougher to turn. Because energy's got to come from somewhere. Brett? Why negative? Tune in to lesson 3. I wrote tune in tomorrow. I'm going to get to lesson 3 today. Example. A circular loop of wire of radius 2.5 centimeters is in a magnetic field of 0.4 teslas. If the loop is removed from the field in a time of 0.05 seconds, what's the average induced EMF? Is there a changing flux? Is there a changing flux? Is there a changing flux? This is a job for Faraday's law. This gets complicated enough that I usually start deficking again. What's N? How many coils of wire are there? Now you have to read this question carefully. They don't blatantly say, but they use a certain word which tells you how many coils of wire there is. Emily, why? Ah, okay, don't forget, they'll do that sometimes. Makes the question easier. Oh, and the other easy one to find is, what's the change in time here? Anyone? 0.05. I'm going to calculate the change in flux. What's change in anything? Final minus initial. By the way, look at the picture. What is the final flux? Flux is magnetic field times area. Do I know the magnetic field? Yeah. Do I know the shape that they gave me? It's a circle. I'm going to have to use the area of a circle, which I think is on your formula sheet on the same page that has the quadratic equation and all that other stuff. I think they do have, do they have pi r squared on there somewhere? Although you should know it, it's on there. So the change in flux is going to be 0 minus magnetic field 0.4 times pi times 0.025, because they gave it to me in centimeters squared. What's the change in flux? I get a change in flux of negative 7.854 times 10 to the negative 4. Not 845, 854. Times 10 to the negative 4. Units for flux, do you remember? The new unit we learned today. Webers. Now let's put it all together. How many volts would be induced by this little, now this is a terrible generator, dropping something out of a magnetic field, but it still works. How many volts? -1. I'll put the 1 in there just so that you know, Joel, that we did include N. change in flux was negative 7.854 times 10 to the negative 4 divided by change in time 0.05. Conveniently, I have this times negative 1 divided by 0.05, and we get about 0.016 volts. Not much. A current would also flow because this is a complete circuit. It's a circle. Not a great circuit, it's a short circuit, but it's a circuit. Which way? We'll come to that. Turn the page. A square coil of wire 5 centimeters on a side has 100 turns. It lies perpendicular to a magnetic field of strength 0.02 teslas. If it's rotated through 90 degrees in a time of 2 times 10 to negative 3 seconds, what's the average induced EMF? I think we're talking about, look up. Initially it starts out perpendicular to the magnetic field, and it's going to be rotated 90 degrees. Can you tell me what the final flux is going to be? Maybe no. They want me to find the average induced EMF. By the way, the reason they keep saying average is it actually changes as you rotate. The flux is changing. It's not a constant value, which again is why we get a lovely sine curve coming out of the plugs. We get an alternating current. We're going to find the average EMF. Well, Joel, what's N in this question? Yep. What's T? Those are the two that are almost easy to find, Joel. .002. Let's see how we do that. We'll pause the recording for a second. The tricky one to find usually, well, it's going to be the flux, the change in flux. I almost always take the time to do this very, very carefully because a number of times, Kara, I've seen dumb math mistakes on this. It drives me crazy. So, over here, change in flux. Kara, what's change in anything? Okay. Oh, we already decided what the final flux was. What was the final flux? Minus BA. What's changing? Well, the amount of area exposed to the magnetic field. Meanwhile, I think we can crunch this. It's going to be 0 minus... Brianna, how big is the magnetic field? Make me look good. 0.02 teslas. Area. What shape did they give me? Now, sometimes they will give you the area, just blatantly. Often they're going to give you, it's either going to be a rectangle, a square, or a circle. They're not going to give you like a dodecahedral area or something stupid like that. What shape? Square. What's the area of a square? Or if you really want to, it's just, since the length and the width are the same, it's the length squared. Yes? So what is the change in flux? Crunch the numbers, please. And then leave it on your calculator because you're going to be using it a short time later anyhow. That, -5 times 10 to the -5. Units, flux, the new unit we learned today, Webers. Now, let's crunch. Negative, what's N? 100. Change in flux, -5 times 10 to the -5, all over. I've seen this was several times a 7-mark provincial exam question. which was really 5 lines worth. It was very nice. I get 0.002. Oh, hey! That's a battery. In fact, that's 2 batteries. That's almost, is it 2.5? Yes? No? Yes? Okay. That's a little more like what's going on here. Okay. A little more like what's going on here. We can also change the flux by changing the magnetic field. So far, we've changed the area, usually from full exposure to 0, or from 0 exposure to full exposure. Since magnetic field is a vector, however, we have to call one direction positive and one direction negative. I like this next question. I like this next question. I like this next question. This next question is a nice question. A circular coil with 100 turns of wire is exposed to a changing magnetic field as shown below. If the field takes 0.12 seconds to change, it looks like it's going from into the page to out of the page. What's the average induced voltage? Is the magnetic field changing direction? Yeah? We have to let one way be positive and one way be negative. Doesn't matter which you pick. I usually let final be positive and initial be negative. Or you can let final be negative and initial be positive. Oh heck, let's let the initial be positive. Let's write our equation. They want the average induced voltage, so we said this. Induced voltage is negative N, change in flux over change in time, where N is going to be 100, time is going to be 0.12 seconds, change in flux is going to be, Connor, what's change in anything? And this time they're not both 0, so I'm going to be a little more careful. Final minus initial. Let's, how about we let this be positive and this be negative. You know what, Mr. Dueck? Don't do that. They'll think it's a charge. Let's write it out. Positive direction. Negative direction. Okay. So this is going to be B final A minus B initial A. And I knew to put the final and the initial on the magnetic fields because that, Emily, is what's changing, yes? The area is staying the same. In fact, the best way to create a generator is you actually do both at the same time. In most generators, you're spinning the coil, but the magnetic field that the generator is inside is spinning in the opposite direction. So you drop the change in time, you increase the change in flux very dramatically. Magnetic field final, we said was negative 5.4 times pi times 0.1 squared minus positive 7.8 times pi times 0.1 squared. Come back. Crunch the numbers. What is the change in flux? Oh, it's a circle. I did pi r squared. I didn't lose you. Did I, Mitch? Okay. You had a change in flux of negative 0.4146, blah, 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 that? Yeah? I'll write negative 0.414, but I'll keep the full value on my calculator, Weber's. And now, here we go. The induced voltage is going to be negative 100, negative 4.414, divided by 0.12, times negative 100 divided by 0.12. Hey! That's a real generator now. 346 volts. That's more than you get out of your plugs. Having said that, these are huge magnetic fields. We said that a magnetic field of 1 Tesla was very big. This would induce a current in here. Which way? Well, hang on. Example 6. So rank the 4 loops below in order of increasing induced voltage. And convince me. Let's see. Which of these would give you the smallest induced voltage? In fact, which of these would give you no induced voltage? Yeah. I disagree. Is there a changing flux? Do you go from full flux to no flux? There's going to be a good voltage there. B. This is what Faraday's brilliance was. He said, Brett, it's not the magnetic field, it's the changing flux that causes the voltage. So B would be 0 volts. Which one would be next? Which one experiences the next biggest change in flux? I think D, because it's squeezed a tiny bit, the area is changing a tiny bit. You would get a small induced voltage. And then which one has a bigger flux, C or A? I think A has the biggest flux. I think, Brett, A would be the biggest voltage. And C would be slightly bigger than D, because I'm noticing they deliberately had more of the area leaving than that small area right there. Okay? When we're talking about induced voltage, for moving wires, it's best to use V equals BLV. For coils, it's best to use EMF, or E equals N change in flux over change in time. You okay? Lesson 3, Lenz's law. So I asked you in the last lesson a couple of times, hey, which way would the current go? And I didn't answer that. What we're going to do is we're going to see, Matt, if we can reason our way to what the answer is. So consider the following situation. I have a coil, here's the side view, and I'm going to move a magnet closer and closer and closer to it. If you want to, you can imagine moving this light bulb closer and closer and closer to this roll of tape. Will there be a changing flux? Yes or no? Yes. So will there be an induced current? Yes, since the change in flux isn't 0, since there is a changing flux. What direction? Well, there's 2 possibilities, and I'd like you to put your pencils down for a second. One possibility, don't write this down, but I'm just going to label it so you can see better. One possibility would be the current could go this way. Now, if that was the case, can all of you hold that solenoid in your right hand with your thumb fingers curling in the direction of the current? Which way would be north, Connor, the left or the right side? That would be north. What would this be then? What would this south pole do to that north pole right there? Attract it. What would happen to this object's speed? Speed up. What would happen to the change in flux? Get bigger. What would happen to the current? Get bigger. What would happen to the magnetic field? Get bigger. What would happen to the force of attraction? Get bigger. What would happen to this? You know what? The universe says, nuh-uh. That can't be right, because that would be free energy. You just have to tap it once, and you'd have a constantly increasing force that would solve the energy crisis. But the universe comes in, and this is one of the times when I'm going to have to just tell you, this is why the universe is saying, nuh-uh. The universe says you can't have free energy. So Emily, what I always ask myself is, which way would resist the changing flux? What would resist a north pole moving to the right? I think a north pole right there. Write that down. A south pole right there. Write that down. And now that you know which way the magnetic field has to be, what kind of a current would create that magnetic field? Hold the solenoid in your hand, pointing your thumb to the left. Which way must the current go? We call this Lenz's law. Lenz's law is not an equation. It's not on your formula sheet. It's an actual English law. It says this: an induced current will always create a magnetic field that opposes the change in flux that created the induced current in the first place. It's awkward to explain in English. It's easier to do with an example. Can you turn back to lesson 2? Specifically, this question right here. Okay? Which way is the final magnetic field that's creating the current? What direction is the final magnetic field that's creating the current? Out of the page. The current that will be created will resist that. What would resist a magnetic field out of the page? Into the page. I'm going to tell you right now, all of you, point your thumbs into the page. The current flowing is this way. Not the other way. It has to be that way. Go back to this diagram here. What current would be created right here? Well, your magnetic field is initially into the page, and then it goes to 0. So it's into the page and getting smaller. What will resist into the page getting smaller, into the page getting bigger? This is a more complicated one. I'm not going to label this one. You're not going to get one where the magnetic field goes to 0, because then it's a bit tricky. But what you are going to get, let's go back to lesson 3 now, please, are questions like this. So, Lenz's law says this: an induced current will always create a magnetic field that opposes the change in flux that creates the induced current in the first place. You get nothing for free, ever, except maybe your mother's love. For some of you. This also explains the negative in Faraday's law. That negative is telling you, oh, by the way, if you're looking for the current direction, it's going to be in the opposite direction of the magnetic field that created the current. Example 1. A loop is placed in a region of magnetic field that is into of the page. How about we cross out the word of? That is into the page. The field then changes direction so that it's pointing out of the page. What's the direction of the induced current? Look at the final magnetic field that's causing the current. What direction is the final magnetic field that's causing the current? Look at the diagram. Out of the page, the current will create a magnetic field resisting that. What would resist that? Point your thumbs into the page. Which way is the current going? Clockwise or counterclockwise? Current will be clockwise. Do you understand why? I showed you why in the first example that it couldn't be the other way, because that would be perpetual motion. The universe would explode. We're not going to go there. Do a couple more. Example 2. This diagram shows an aluminum ring, and it shows the current induced in it. So I know the direction of the induced current. This magnet must be stationary, moving to the left, moving to the right, or spinning. Okay, now this time I know the direction of the induced current. Which way is the induced current moving? This way. Hold that in your hand, curling your fingers that way. Which way is the induced north pole? To the left or to the right? So let's put a little north pole right here, a little south pole right here, and now ask yourself, this must have been caused to resist whatever was happening here. A north pole right there would resist what type of motion? South pole doing what? Moving away. This must be moving that way, because if the south pole is moving further, you do have a changing flux, it's going to create a north pole trying to tug it back and slow it down. That Lenz's law, that's the force that I'm feeling right now. It is resisting the magnetic field that I'm creating by causing the current, by inducing a current. This has to be moving to the right, because a south pole moving to the right is what would cause a north pole to tug it back. If the current had been going in the opposite direction, I have a south pole there, then I would say, oh, they must be pushing it to the left because a south pole would resist a south pole moving towards it. You gotta kind of use your imagination here, Joel. Lenz's law, it's an English rule. Example 3. Will the induced current in the circuit below flow through the 15 ohm resistor from X to Y or Y to X? I don't know. What direction is my final magnetic field that's causing the current? Out of the page? So what direction will this create a magnetic field? What would resist the magnetic field out of the page, Brett? What would resist the magnetic field? Here's our after. What would resist the magnetic field coming towards us out of the page? Point your thumbs into the page. Which way must the current in the coil be going? It must be going this way. It must be going this way. It must be going this way. Now follow it through, follow it through, follow it through, follow it through. Which way are we going through the resistor? From Y to X or from X to Y? Lenz's law. Example 6. If we are moving the magnet to the left, so specifically I look at the pole that's closest to the coil, I have a north pole moving to the left, that will change the flux, because that's the same as doing this. Is the amount of light going through my roll of tape changing? Yes. Will the amount of flux going through this coil change? Yes. What direction will the current be? Which way is this north pole moving? To the? What would resist a north pole moving to the left? What would oppose that? A south pole right there, tugging it back. See it? Which would mean the north pole is over here, which means which way am I going to point my thumb for this solenoid? To the right. Which way is the current coming? I think it's coming this way. Lenz's law. It says, Mr. Dueck will now show you a demonstration that's as close to magic as you'll ever see, unless you know about Lenz's law. Homework from the Ultimate Induction Unit Review. These are the questions that you are now capable of doing. Number 1. If you can't find it right away, you can just write these down at the bottom of lesson 3 and then fill them in. Number 1. Number 3. Number 5. Sorry, number 4, not number 3. Number 1, number 4, number 5. 6. 7. Which somehow... Do you guys have answers for number 7? Did your question get chopped off? Yeah? Okay, I guess not number 7. 8. You can now do. 9 you can now do. Here's a Lenz's law kind of a question. 12 you can now do. 15 you can now do. 16 you can now do. 18 you can now do. Remember, for a rod, use voltage equals BLV, but for a coil, use the new EMF equals N, change in flux over change in time. 22. Here's a classic Lenz's law. In fact, this is what I was just doing with you guys. This is what's going on there. 23. 24. 25. 27. 30. 32. 34, 35, 36, 37, 39, 40, 43, 46. The scholarship ones are cool, but I'll omit those for now. So we got our 2 lessons done today. So if you look at the schedule, you can move this to Thursday, to Tuesday. We can do our test Thursday. It'll give us a review class or review period. Okay? Or you know what? It's up to you guys whether you want to have the test there and have a final exam review day. We'll talk when we get closer. I'm flexible either way.